So this is where we left off in our previous lesson, where we talked about defining sine, cosine, and tangent, the inputs of those three trig functions as angles, and then the outputs as ratios from the xy plane. Previously, you defined the outputs as ratios of the sides of right triangles, but that's very limiting for the number of angles that you could evaluate the trig functions for. So if we think about the outputs as being ratios from the xy plane, where x and y represent coordinates, and then r represents the distance of a point to the origin, that's going to allow us to think about evaluating all of the trig functions for more angles than just angles that are less than 90 degrees because they're angles from a right triangle. So to help you understand this, I have the little picture here. Now, an angle that's in standard position starts on the positive x-axis. Here's the x-axis, here's the y-axis. And then this angle rotates in the counterclockwise direction, which creates a positive angle. And the terminating side of the angle continues on forever into the xy plane. And it crosses or intersects the unit circle at exactly one point. Now that point we're able to say is can be represented as cosine theta, comma sine theta. And that's partly, we derived why that is, but that's also partly because any point that lies on the unit circle is a distance of 1 unit from the origin. So r would be equal to 1, meaning that cosine of theta would just end up being equal to the x coordinate because r is equal to 1, and sine theta would be equal to the y coordinate because r is equal to 1. But there are infinitely many points on that terminating side of the angle. You can choose any of those points, and then if you find the distance to the origin, you could also come up with the ratios for sine or cosine or tangent. And then those three main trig functions also have reciprocal trig functions. So the reciprocal of sine is cosecant, and that's spelled C-O-S-E-C-A-N-T, but it's abbreviated as CSC. And that's the reciprocal of sine. Notice that their outputs, the ratio, is just flipped. The reciprocal of cosine is secant, abbreviated as SEC. And then the reciprocal of tangent is cotangent, abbreviated as COT. And we'll talk more about like the names of them when we talk about the cofunction identities coming up here. But cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So these statements are also true. Cosecant is equal to 1 over sine, secant is equal to 1 over cosine, cotangent is equal to 1 over tangent, but is also equal to cosine over sine, since tangent is equal to sine over cosine. So next we're going to talk about radian measure. So radian measure is a ratio of the arc length of an angle over the radius or the length of the radius of the circle that you could draw that would intersect the initial and the terminating side of the angle. So in this picture, you can see S represents the arc length. And then R represents the radius. And S and R have to be measured in the same units so that those units cancel. And then whenever an angle is represented in radian measure, it just, because the units cancel, it represents a real number, which is really handy for a lot of different situations that trig functions can model, where we don't want to think of the input necessarily as an angle, and we want to think of the input maybe as like time or something else, but it allows us to use the trig functions to model other types of situations. It also will eventually allow us to graph the trig functions in the xy plane so that our x and our y-axis represent real numbers or real number lines. So we're going to derive all of the angles that are on our unit circle. We're going to write them in radians. They're already written there in degrees, and we're going to write them in radians. But in order to do that, let's look at what a full rotation, so 360 degrees, what that is in radian measure. And that's going to allow us to then determine what the other angles are that are on the unit circle. So a reminder that the circumference of a circle is equal to 2 pi r, right? Or that's diameter times pi. So for a full rotation of 360 degrees, that means that the arc length would be equal to 2 pi. So if we're trying to determine what 360 degrees is in radians, and in radians, the angle would be the arc length divided by the radius. The arc length for a full rotation of 360 degrees would be 2 pi r, where regardless of what r is, r will cancel, leaving us with 2 pi. So 360 degrees is equal to 2 pi radians. You might see 2 pi radians written out, 2 pi rads, or just 2 pi if nothing's written. So that's where it's really important to, whenever you want an angle to be in degrees, you need to have the little degree symbol up to in the right corner of the angle. And if you don't see a degree symbol, you're assuming that the angle is in radians. So to go through and fill out the values of these angles in radians, 0 degrees is going to end up being 0 radians. And we just said that 360 degrees is equal to 2 pi radians, which means that 180 degrees would be half of that, and it would be pi. 90 degrees would be half of 180 degrees, which would be pi over 2 radians. 30 degrees is 1/6 of 180 degrees. So we could write 30 degrees as pi over 6 radians. 45 degrees is 1/4 of 180 degrees. So we can write 45 degrees as pi over 4. And 60 degrees is 1/3 of 180 degrees. So we can write 60 degrees as pi over 3. And then similar to how we determine the rest of the angles in degrees on the unit circle, we can start at like pi over 6. And we can just think about adding pi over 6 as we go around. So pi over 6 plus pi over 6 would be 2 pi over 6, which simplifies to be pi over 3. And then if we add another pi over 6, that would land us at 3 pi over 6, which is pi over 2. And then if we add another pi over 6, that would be 4 pi over 6, or 2 pi over 3. And then adding another pi over 6, that's 5 pi over 6. Pi is 6 pi over 6. 7 pi over 6. 8 pi over 6 can be written as 4 pi over 3. 9 pi over 6 can be written as 3 pi over 2. 10 pi over 6 is 5 pi over 3. And then 11 pi over 6 and 12 pi over 6 is 2 pi. It works the same So like pi over 3s, if we were to think about adding pi over 3, 1 pi over 3, 2 pi over 3, 3 pi over 3 is pi, 4 pi over 3, 5 pi over 3, and then 6 pi over 3 would be 2 pi. So looking at pi over 4s and thinking about adding pi over 4s as we go around, pi over 4 plus pi over 4 would be 2 pi over 4, which is pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4 is 2 pi. So those are our angles that are on the unit circle in radians, and you should know those as well. I think those are actually easier to visualize. So we're also going to talk about how you can convert, because you can go between degrees and radians, but you do want to get comfortable with both. Like you don't want to have to convert to degrees and back to radians, and that it would be pointless for bigger problems to try and do that. And just very challenging. So you need to get comfortable with both. So in order to convert from degrees to radians or radians to degrees, you could think about setting up a proportion and then solving. But to convert from degrees to radians, you're going to multiply by pi over 180 degrees. And that's because 180 degrees is equal to pi radians. And then to convert from radians to degrees, you're going to multiply by 180 degrees over pi. And okay, so in order to go from 60 degrees to radians, we would multiply 60 degrees by pi over 180 degrees. And that would end up being pi over 3. And the degrees would cancel. And then to go from 460 degrees to radians, that would end up being (23 pi over 9). And to go from 3 pi over 2 to degrees, we would multiply by 180 degrees over pi. In this case, the pi's would cancel. And then that would end up being 3 times 90, which would be 270 degrees. So it's the same to evaluate the trig functions for angles that are radian and radian measure. You're still referencing the unit circle in the same way. So if we want to evaluate sine of 2 pi over 3, we're visualizing the unit circle and where the angle 2 pi over 3 would terminate, which is in quadrant 2. Sine corresponds to the y-coordinate, so sine of 2 pi over 3 would be equal to root 3 over 2. Cosine of 5 pi over 4, well, 4 pi over 4 would be pi, so 5 pi over 4 terminates in quadrant 3. And the point that corresponds to that angle would be negative root 2 over 2, comma negative root 2 over 2. So the x-coordinate would be negative root 2 over 2. And then tangent of pi, I'm thinking about where pi terminates, which is the negative x-axis. And the point on the unit circle that corresponds to pi would be negative 1, comma 0. Tangent is y over x, or sine over cosine, which would be 0 over -1, or just 0. So an angle is formed when a ray is rotated around its endpoint. The common endpoint is called the vertex. And the ray in its original position is called the initial ray, or the initial side of the angle. So in this picture, we've talked about this a little bit. This would be the initial side of the angle. And this would be the terminal side. The ray after it's rotated is called the terminal ray of the angle. If you rotate an angle in the counterclockwise direction, it creates a positive angle. And if we think about rotating in the clockwise direction, it creates a negative angle. So thinking about, it's good to be familiar with visualizing where angles terminate, because we talk a lot about where different angles will terminate and what that means for the trig functions when they're being evaluated at different angles. So 400 degrees is more than one full rotation. Let's see if I can draw a picture here. .400 degrees would be rotating in the counterclockwise direction because it's a positive angle. It would go more than one rotation, since one rotation is 360 degrees. And then that would be 40 extra degrees into quadrant 1. So 400 degrees will terminate in quadrant 1. Negative 150 degrees is rotating in the in the clockwise direction because it's a negative angle. So we think of it starting on the positive x-axis and then rotating in the clockwise direction. And negative 180 degrees would end up rotating all the way to the negative x-axis. But negative 150 degrees will end up terminating in quadrant 3. Okay, 7 pi over 12 is not an angle that's on the unit circle, but we can figure out where it terminates. Now, pi over 2 can also be thought of as 6 pi over 12. And then pi can be thought of as 12 pi over 12. So 7 pi over 12 will start on the positive x-axis, rotate in the counterclockwise direction, and will end up terminating in quadrant 2. And then negative pi over 2 will be rotating in the clockwise direction, okay, starting on the positive x-axis, and it will terminate on the negative y-axis. So it's actually not terminating in a quadrant. It would be terminating on the negative y-axis. That would be the best description for where that angle ends. So coterminal angles are angles that terminate in the same position. And every angle has infinitely many coterminal angles. And you can determine an angle's coterminal angles or additional coterminal angles by thinking about adding or subtracting multiples of 2 pi or multiples of 360 degrees. So coterminal just means that they terminate, they stop in the same position. So we actually just looked at an angle that's coterminal. We looked at a couple different ones that are coterminal to angles from the unit circle. So like negative pi over 2 this angle, negative pi over 2, is actually coterminal with 3 pi over 2. They terminate in the same position. And if we were to add 2 pi, so adding 4 pi over 2 to negative pi over 2, we would get 3 pi over 2. And again, every angle has infinitely many coterminal angles. Infinitely many angles that terminate in that same position. So to find the measure of the smallest non-negative coterminal angle of a given angle measure in degrees, then you're going to subtract 360 degrees repeatedly, or take a multiple of 360 degrees to subtract. If the angle that's given is negative, then you're going to be adding 360 degrees or multiples of 360 degrees. And then if you're in radians, you would be adding or subtracting multiples of 2 pi. Now, this can be helpful to us if we're wanting to evaluate the trig functions for angles that are not necessarily angles we think of on the unit circle, but if they're angles that are coterminal with angles on the unit circle, then because they terminate in the same position, they're going to have the same ratios or the same values for x, y, and r. So we can evaluate any of the trig functions at an angle's coterminal angle, and we'll get the same output. Let's first just practice finding the smallest possible positive coterminal angle, right? Because every angle has infinitely many coterminal angles. You could think about just subtracting 360 degrees or 2 pi over and over and over again, but it can be helpful to find the smallest possible positive coterminal angle. So the angle that would lie between 0 and 360 degrees, or 0 and 2 pi. So for 900, if we subtract 360, that just lands us at 540 degrees. So we could also think about subtracting 720 degrees. And then that would land us at 180 degrees. So if we subtract 720 degrees, we get 180 degrees, which means that 900 degrees terminates in the same position as 180 degrees. They are coterminal angles. For negative 430 degrees, if we add 360, we're going to still be in the negatives. So let's add 720 degrees again. And then that puts us at 290 degrees. And then for negative 13 pi over 6, if we add 2 pi, that's adding 12 pi over 6, we would still be in the negatives. So let's actually add 24 pi over 6. Which would end up being 11 pi over 6. So negative 13 pi over 6 is coterminal with 11 pi over 6. So using coterminal angles, we didn't talk about reference angles. Sorry, this is from another lesson. We're going to use coterminal angles in order to evaluate the trig functions exactly. Now, these angles are not angles that are on the unit circle, but they are coterminal with angles from the unit circle. So sine of negative 480 degrees, if we add 720 degrees, we get 240 degrees. So this is equal to the sine of 240 degrees, which sine of 240 degrees is equal to negative root 3 over 2. Right, you could reference your unit circle, 240 degrees, the y-coordinate. (23 pi over 6). We can subtract 2 pi. And we get 11 pi over 6. So cosine of 11 pi over 6. 11 pi over 6 is an angle on the unit circle. would be positive root 3 over 2. (900 minus 720, we already said that was 180 degrees. Secant is the reciprocal of cosine, so this would actually be equal to 1 over cosine of 180 degrees, or you could just think about, okay, at 180 degrees, cosine is equal to -1. The reciprocal of -1 would just be -1. And then cosecant of negative 10 pi over 3, well, if we add, if we add 2 pi, we haven't gone far enough. So let's add 4 pi, which would put us at 2 pi over 3. Cosecant is the reciprocal of sine. So this is equal to 1 over sine of 2 pi over 3. I'm thinking about the y-coordinate at 2 pi over 3. That's in quadrant 2, where sine would be equal to root 3 over 2. So the reciprocal would be 2 over root 3, which then if we rationalize the denominator, let me shrink this down. If we rationalize the denominator by multiplying by root 3 over root 3, we get 2 root 3 over 3. Okay, so knowing the coterminal angle of an angle, or identifying a coterminal angle of an angle, can help us with evaluating the trig functions for angles that lie or are coterminal to angles that lie on the unit circle. Okay, now I think I'm going to leave this part for a second.